Methyl propanol.
Yeah, you really did. No, butanol.
Oh,
Butanol. Three methyl butanol.
Butanol, yes. What was the ending for ketones? Great job. What about esters? OH? Okay, now we're going back to chapter 9. Very simple question. How many signals in H&MR do you see?
Four.
Do we all agree? Just 4? Yes, you guys are absolutely correct. So we have signal 1, we have the 2 hydrogens in here, the baby one, and those guys are 4. How many CNMR signals do you see? It is also 4. In H&MR, which signal is the most de-shielded? You have the signals labeled in there. Yes. Which one is the most de-shielded signal? De-shielded.
Shielded for what? CNO or
H&MR.
either way, it's the one bearing is probably one.
This guy is your most de-shielded. Which one is the most shielded?
Oh, wait, three.
4.
Wait, H and one? Yes.
Yes.
because it looks electron density outside. Because that eight, because 3 has 1 8. That electron.
It's a little unprotected. There's more. The further away you are from something that's electron dense, the more shielded you are. So the method groups are further away. It's not about steric hindrance. Okay, how do we know that something is de-shielded? What were the factors?
Close to an electronegative atom.
Mm-hmm.
Because I know like always just like pretty one like
Exactly. So whenever you're close to something that's electronegative or electron dense, you're going to be de-shielded. What's the approximate chemical shift for the most de-shielded signal?
I think these two is like higher.
I need a number. I hear 8. And Emily, what do you say? 10 to 12? Yeah, what's the ppm range for signal 1, the most de-shielded one? I have one vote for 8. Yes. And we already determined that it was signal 1. So what's the ppm value? 17? Yeah, a little too high. But it's actually around between 9 to 10 ppm. What about signal 4? Around 2, yeah, around 1 to 2.
These two is like higher up.
Mm-hmm. Okay, what about multiplicity now? What's the multiplicity for signal 1? It's just a singlet. Signal 2.
Wait, no, triple.
Wait, hold on.
Because that one,
Why
why
is
is
it a
it
single?
H on the carbon?
It's a triplet, yeah, I agree.
Oops, sorry. I gave you an aldehyde, not a ketone. 1 bond away, carbon. 2 bonds away, carbon. We touch the hydrogens in here. You can't go through heteroatoms, but right now I'm just going through carbons. I'm not going up to the oxygen, never touching it. So I can keep going to the right. Multiplicity for signal 2. This split by 2. Exactly. What about signal 3? Multiplicity. We're just gonna call it or non, yeah. Signal 4. It is a doublet. What was the definition of integration?
Area under the curve.
The number of protons in a signal.
Mm-hmm. So yeah, that's where you can find integration, yeah, but the definition is that it's the number of hydrogens.
That's the.
What does it mean to have spin-spin splitting? Spin-spin splitting. If you weren't here, do not say it. A molecule is showing spin-spin splitting when?
Isn't it when it's like, it's.
It wasn't the practice final. Best guess. What do we think? We're showing the tree. Okay, that's showing multiplicity. The J values. A singlet. So whenever a molecule has something more than just a singlet, so we have a doublet, that molecule is showing spin-spin splitting. But if we just have pure singlets, that molecule is not showing spin-spin splitting. Okay? Simple as that. It just sounds funny.
So I asked him why it's the sugar for the first one, sugar for the second one. Why is it double for?
Say that one more. Once again. Say it again. Why is number 4 what?
A doublet.
A doublet because it has only one neighbor. 1 + 1 is 2. The only neighbor is the little baby hydrogen in between. Mass spec. What happens when we put a molecule through the mass spectrometer? It breaks it into little fragments. Okay, we had 4 main peaks, right? I'm waiting for a yes. Yes, okay, good. The base peak. Where can we find it? Tallest one overall. What does it represent? That's where we can find it. The tallest one. But what does it represent? Base peak. Most stable fragment. Exactly. What about the M+ peak, the molecular ion peak? Where can I find it? To the right.
It's like right next to
Mm-hmm. What does it represent?
The entire molecule.
What about the entire?
The original.
The
molecule.
weight of the original molecule. Mhm. What about the M+ peak? What happens if it's an odd number? Odd number of nitrogens. What does the M+1 peak represent? It represents the presence of carbons, normal carbon, the isotope of carbon, and that's a major contributor. M+2, it can represent 4 different atoms, but which one was the major contributor? It was bromine. Bromine, then chlorine. What were the last 2? Oxygen and sulfur. There you go. You have to remember those guys. So, chapter 9. How do we know we're doing complex multiplicity? That's one of them, yeah. Or it says in theory. Yeah, simple as that. Plus also, you can pretty much figure it out based on the answer choices you're given, which is just in numbers.
Can we do one of the complex multiplicity?
Yeah. This one. Okay. Let's look at that little molecule composed of pure carbons. Let's just pretend that there's a long paragraph in there that basically says that the J values are not equal to each other. What's the multiplicity for signal B? Multiplicity for signal B. if the J values are not equal to each other. How do we solve it? N plus 1 times n plus 1.
We're using the plus 1.
That's the formula for complex multiplicity. Normal multiplicity was n plus 1, but complex, it's n plus 1 times n plus 1. Now what? What am I going to plug in? What's going to be the n value for the A signal? What about C? It's just 2. Do we see it? We're just counting how many hydrogens we have per signal. Do we see it now? Okay. What's going to be the multiplicity? Beautiful.
21.
That's it. Yes.
Why do we?
Single bonds, they constantly rotate. So at the end, they're both the same signal. No. You count every hydrogen that's part of the signal. For everything there.
Yeah, and it also displays.
Yeah. Oh, that reminds me. We had 4 terms in chapter 9 when we were talking about relationships between hydrogens.
It's,
What were the what?
we're talking about like integration and like.
No. Those are the aspects for H and MR.
Oh,
Whenever we're comparing two hydrogens, when we want to talk about their relationship, we use 4 different terms, which are
oh,
Yeah.
yes. Okay, so let's go through each of them. So we just have, let's write it down actually.
so homotopic, heterotopic,
Mm-hmm.
diastereotopic.
And we have an enantiotopic. Okay, what was the definition for homotopic hydrogens?
Identical statement.
They're just the same signal, identical. Heterotopic, just different signals. Enantiotopic, bless you.
Was this where the Q test comes in and it's like where you plug in a X halogen or whatever, and if you get RNS configuration, then yeah.
Exactly, whenever you're able to form a possible chiral they are an enantiotopic. What about diastereotopic? We had 2 different scenarios. In that case, you have an established one and you form a possible one. That was the main difference. So established and possible. What was the second scenario? It has to do with double bonds.
EMC?
E and C. Okay, so far, are we starting to remember those terms? A little, somewhat? Okay. Okay, it seems like most of you are not that sure. That's okay. So let's practice this.
But it's relative to the two hydrogens that you're comparing.
It's always only related to two hydrogens that you're comparing. But in this case, I'm gonna recycle the same molecule. We're gonna label that one HA, for example. This one HB. What's the relationship between HA and HB? They're just in completely different signals. They're just heterotopic. HA and HC. They're just homotopic.
Yeah.
They're part of the same signal. Simple as that. Okay, now, before we keep going with the relationships, do we see any established chiral centers in the molecule? We see one, which hopefully you just saw it over here. Do we all see it?
Yeah.
Okay, what was the definition of a chiral center? What do we have to look for? A carbon with 4 different groups, exactly. Okay, so we have established one. So if we keep doing comparisons, we might be able to have distereotopic hydrogens. Okay, so keep that in mind. Let's compare now. Let's compare HB and HD. What are they to each other? They're just heterotopic. Could any of those hydrogens be distereotopic to each other?
Like where HA and HG were was another methyl instead of like it ending there, would HG be an H like
Then those two would be distereotopic.
yeah.
Yes.
One would be the names of those. Or I
Okay, let's do one that's in antitopic over here. Okay, so okay, same process. HA and HB relationship. Why distereotopic? You're correct, Mickey. You're forming a possible chiral center and you already have one. Where's the chiral center? The established one. So these two guys are just distereotopic. Now let's use the same carbon skeleton, but let's modify it slightly. Okay, now what's the relationship between HA and HB? Do we see it? Okay. They are an antitopic because we are only forming a possible chiral center. We don't have anything that's established. So. A small difference can make a big one. So keeping that in mind. So far, questions on the relationships. We're okay? We're not okay? Oh, I forgot about J values. Yeah, you're right. Actually, if I'm being quite honest, I really doubt that you're gonna get J values on the final. I really doubt it. Yes. You guys just got so relaxed. But yeah. That's J values. I don't think it's gonna be on the exam. Because mostly he's gonna want to test you on mass spec, HNMR, and CNMR. Those are like the core concepts. We did talk about mass spec though. We did talk about mass spec. We briefly reviewed that. No, mass per charge. Yeah, you're talking about that. Okay, so far questions on chapter 9. We're good? We're starting to remember it? How comfortable do we feel with chapter 9? Just based on this. 8 out of 10? Kinda, okay, we're kind of good. For the final review, do we want more questions from chapter 9?
Questions from the all the chat.
I have to balance out the questions, so.
Yeah, I think I get like an even amount.
Okay,
Yeah, he showed us a little chart where it says 7 questions from 9.
Yeah.
10. Did you see that?
yeah, that was at the very beginning.
Yeah, they're like.
But yeah, I mean, I'm not gonna do 64 questions for the review. We only have 2 hours.
Yeah.
We did
Well,
43 in 3 hours. Yeah, but I have to explain it. So, yeah. So I'm trying to see which chapter is the worst one, so we can do that one the most. Everyone says 11 and 12. Does everyone agree? 11 and 12?
Wasn't that SN?
We don't remember 11 and 12?
No,
We do? Okay. Okay, let's start reviewing 11 and 12.
What was 10?
Radicals, but that's from Orgo 1.
Okay, okay.
So yeah, you don't have to worry about it. Yeah, we're just skipping that one. 11 and 12. What were the 2 ways in which we can name ethers? How do we name ethers? There were 2 different ways.
Like cyclic Easter.
Ester is not the same as ether,
For some reason I heard Easter.
not esters.
Yeah, that's like later.
That's a type of cyclic ethers. The oxy one. Oil, that's for alcohol groups. But for ethers, we can either just say literally just ether, because that's your parent chain, or when you have some carbon chain that's branching off, then we use the ending oxy. Okay, ox. Okay, we're definitely gonna practice this on the up all night.
No.
Like questions just plain asking for the name? I don't think so. I think that he might give you the name of the molecule and then ask you for the product of a reaction. So yeah, he has to combine everything in a few questions. So yeah, get ready for it. Might be a lot. But next part was boiling point. What was the trend for boiling point?
Hydrogen bonding.
There you go. Yes, that has to do with the intermolecular forces. What was the strongest force of all?
Hydrogen.
Hydrogen bonding. Next one. Dipole. Last one.
London dispersion.
Yes. London dispersion forces. Van der Waals, yeah, same thing. Why they have different names, no idea, but yeah, right. What about the trend between boiling point and molecular weight? What's the relationship? Okay. How do we name crown ethers?
12 crown. No, 12 crown.
big number,
Four.
number. Or oxygen.
Oxygens times 3. It's okay. We're here to learn. We're here to review.
Was it 3 crowns? No, you said multiply by 3, so 3 crown 9.
It was number crown, another number, ether. The first one was the big number that represented the number of carbons and oxygens. The other one was the small number representing just number of oxygens. You just count. That was like everyone's favorite question. So yeah.
It would have
So,
been a
yeah.
very question, and then you put the numbers on.
Okay, let's talk about reductions and oxidations. How do we know we're doing a reduction?
When it gains negative
What was the orgo definition?
gain of
When you lose carbon to oxygen bonds. Exactly, you're decreasing the amount of carbon to oxygen. So that means going from a carbonyl to an alcohol group. What about oxidation? Carbon and oxygen. Okay, what were the two main reagents that we use for reduction? What? The sodium and the lithium reagent, yes. So let's
lithium
just
is high,
NaBH4. What was the main difference between those two?
much stronger.
Which one's strong?
Lithium.
Okay, but what does that mean?
Because lithium is like a battery, like that energizer.
Just with ketones? Okay. Ketones and aldehydes. So we can only react with ketones and aldehydes. But why? Why is that the case? Why not with the esters? Think about, no, you guys have to know the logic behind it. Think about reactivity of carbonyls. It's something that we always talk about. Something hindrance. It's all about steric hindrance. The less steric hindrance, the smaller you are, the easier it is to attack. So ketones, aldehydes, they're really small. So we can just use the weak one. But for esters, carboxylic acids, they're bulkier. So we need something that's stronger. What was the nucleophilic species for reductions? Just hydrogen? The hydrogen that had? It's the hydride. So that means hydrogen with lone pair and your negative charge. Okay. Now
You
for,
said that was the what?
that's the nucleophilic species, the one that does the attack. So H minus, nucleophile. What's going to be the electrophile for a reduction? We've seen it in a lot of reactions. The carbonyl, exactly. We have the dipole moment. Delta positive is in the carbon, so that's my electrophile. Okay, so oxidation was very similar, but we had a lot more reagents, right? Now, we had weak and strong. The weak ones, we only had two. What were the weak oxidizing agents? PCC. That's a protecting group. The one that has DMSO. It was the really long one. What's dibel?
Diisobutane. Aluminum. I forget that.
It's okay. You don't have to know the full name of dibel. But what kind of reaction did dibel trigger? It makes the ester into an aldehyde. So what's that? Oxidation reduction? It's a reduction. We lost that one between the carbonyl and the oxygen in the leaving group. So technically we can write dibel over here. What was another kind of reduction that we could do? We can use dibel, we can use NaBH4, the lithium reagent. Some of you called it the Grignard reaction. Grignards. Grignards. It's the one with MGBR, exactly. That goes away and you're left with a nucleophile that has a negative charge. So that's going to be attacking.
So just to reiterate, so the sodium borohydride, aluminum, lithium aluminum hydride, that's two reduce,
Yes.
right? One's weak, one's the other one, right? Esters, right? So that's the to reduce, and then we're talking about oxidation. So PCC,
PCC and DMSO, those are weak oxidizing agents. Yes, those were the easiest ones to memorize.
everything that had CLs in it, right? Or what was that? It's O's.
There was something in particular about strong oxidizing agents.
Had a bunch of
A bunch of, a bunch of oxygens. Yes, that's it.
chromium something.
Yeah, something with chromium was there. Yeah, there's a few options. Okay. Who wants to do the mechanism? I want to do? What? Best try. Just draw whatever you think it's correct for the mechanism or what the product is.
Okay. That's 4. So I know that this is a weak one, and it's
Mhm.
abduction.
Mm-hmm.
So that means that we're probably gonna lose this right here. eh.
So you're correct. It's a reduction. So we go from a carbonyl.
I guess this body will break apart then.
It's gonna break apart, yes, because remember, what was the nucleophilic species for reductions? Whatever hydrogen
Yeah.
comes from the reducing agent. So that deuterium
So I guess.
attacks. Beautiful. And then we get up electrons.
Oh, I just done it for a recent one actually.
And there you go.
So now how do I draw the product?
So far, keep the legs of the ketone.
Okay, got that. And then I got the
One more, there you go. And then oxygen minus because we kicked up the electrons, beautiful. And then the deuterium got connected to the carbon in there.
So, okay. Okay, so I guess I'll just put this now.
And deuterium, beautiful.
Okay, so
So-
that's basically it, right?
That's basically it, but we don't like charges. We want something that's non-reactive. So
This goes back here.
does it go back there?
Oh,
Remember, reductions, we want to go from a carbonyl to an alcohol group.
right. I mean,
So we
Is that-
just need a little hydrogen.
is there like a race button here?
Oh, yeah, no worries.
Yeah, but okay, so that's the first step. I got the first.
So
step.
yeah, you're absolutely correct. So still a great job. So that oxygen is just gonna,
Oh, so
attack.
there, okay. Just
and
that.
there you go, that's
Okay.
it.
Yeah, but I didn't get the first step correct.
And that's the most important one, so still, great job. Do we remember this mechanism? Okay, we do remember. We need coffee, that's okay. Let's do another reduction, but with
Oh,
it's Grignard's. Mechanism wise, it's very similar. Want to do it, Mickey? Go for it, Mickey.
Oh, I see, we're just attaching that.
And there you go.
And Grignard works for both ketones and aldehydes.
Grignard's works with almost everything. What was the exception?
That's-
Yes, great job, Mickey. You got it.
Wait, what was it?
Grignard's is a reduction. Reductions, we can do them with carbonyl groups, right? Okay, now the lithium reagent was a strong one. That one can go with any carbonyl, esters, carboxylic acids, but Grignard's couldn't do the reduction for anything that's acidic. So a carboxylic acid, for example, that's not going to be able to work. So yeah, What would happen if I have a carboxylic acid and I have Grignards? It's just an acid-base reaction.
Yeah.
Simple as that. When is the only exception where I could proceed with a reduction? Same scenario. What would you change to make it happen into a reduction? It's okay. What was your question? Oh, sorry. I thought you wanted me to square. But yes, give me 1 second. Mm, There you go. So yeah, it's not too bad. Let's see what's gonna happen now.
This looks almost identical to a question.
That's good though. That's good. But now let's see what happens if I want to do a reduction of an ester with okay. That it's a phenyl group. Huh. You got it, Mickey. Okay, who wants to give it a try?
This is a trick question. It's gonna be like no reaction. Something like that.
Is it?
It could.
When is it no reaction? Do we have anything that's really acidic in there? Okay, the alpha hydrogens are acidic, but they're not as acidic as an alcohol group, for example. Yeah. Now that we know alpha hydrogens, we can say that, yeah. Something more acidic than alpha hydrogens. Mickey. Wanna do it? Okay, show me the mechanism. Okay. And there you go. And the VR goes away. Nucleophilic attack. Pick up the electrons. What are we gonna kick off? You reform the carbonyl and then you kick off that oxygen. That's your leaving group. So far, what are you forming? That car.
Oh, no, that's right.
Yes, so far you're good. Okay, now, but again, Grignard's is a reduction. I don't want any pi bonds. So what happens? It repeats again, yeah. So that phenyl group is gonna come again and it's gonna attack carbonyl, pick up the electrons.
Is there a specific, I guess, notation where it says excess Grignard's?
You can pretty much just assume that you have Grignard's unless you have some sort of acidic situation.
Right.
It can work if you're given excess of the Grignard's reagent.
For an acidic.
Yes, you can technically override it. And then how do we make everything more stable, more neutral? How do we get rid of those negative charges? Water is gonna come again to protonate it.
Wait, but
Oh yeah, sorry, water wasn't given. Let's just assume that it was given. Yeah, it's just water. And there you go. Great job, Mickey. You got it. Okay. Yeah, I forgot to give you water. That's what happens when I come up with my own problems. So yeah. Okay. Epoxides. Epoxides are reactive in acids and bases. What about any other ethers? Only acids,
Yeah.
not on bases. What was the ranking for acid cleavage?
Depending on your class.
What about West? 3, 1, 2. Bases. 1, 2, 3. Simple as that. Okay, so let's do one last one with epoxides.
And this is still chapter 11, 12?
Yes, it's still 11, 12. The thing that everyone hated. So the 18 and the deuterium, they are isotopes. They're specifically there to test you where to cleave and what exactly you're adding. Wanna do it? Yeah, you had a very similar question on the practice final. So who wants to give it a try? Okay, one. Go for it. So far, so good.
I guess the hydrogen would get picked up by that.
Remember that the H plus or HA that you're given on the arrow, that's just indicating that water is acting as an acid. The main reagent is going to be the water that's deuterated at the bottom. So far, you're good. You broke that bond between the oxygen and primary carbon. No, the primary carbon, that's CH2, it's still there. You didn't get rid of the 2 hydrogens in there. Now, that carbon lost 1 bond. So we have a positive charge in there. We just created a
So
carbocation. There's a little carbocation. Okay, now.
Okay, so then it would be, this would. That,
We can do that, yeah. Or
or,
we can use any hydrogens, technically. And remember, H plus, that one is just there to indicate you that water is acidic. We don't really have H plus.
so would it be? D
So,
plus?
D. So oxygen attacks, takes it away. Okay, so we fixed one of the problems. We neutralized that oxygen. So now we have OD. Because it lost 1 bond. We cleave that bond between oxygen and primary carbon. H plus is just to indicate that the water is acting as an acid. If it wasn't there, it could be either or. Okay, we fixed one problem. How do we fix the positive? Is it just normal oxygen? Oh, 18, beautiful. You got it. Great job, Juan.
Hold on, just walk me through what I did though. So it's, okay, I get the 3-1-2 cleavage with an acid. It'll be 1-2-3 in a base, but we're acidic. Cleave that, so you're left with that. if we have free floating hydrogen, why wouldn't it just come and hit that HO?
I mean, technically you can do that, yeah, but technically you can have two different products. One where the oxygen on the side that you didn't cleave has a normal hydrogen, the other one can have a deuterium. Because technically water is just giving it access, so. But
Okay.
just for the sake of it, H plus is just indicating the acid. It's not really participating there. Let's just focus on the water.
Okay,
That's the actual active reagent, Nikki.
right, because then you would.
This O or the other O? For acid, it's confusing because you go from something that's really substituted to something that's not substituted to something that's mediumly substituted. Because remember, the ranking was 3-1-2. So there's no really logic behind that one. Dr. Roche says that it's based on the steric hindrance, 3-2-1. But for this case, let's just use Wes's ranking. Yeah, but either way, hopefully you guys are starting to remember. I'm gonna try to make a handout if my computer works by Friday. So we'll see. I'll see you guys Friday. And that's the last essay session of the semester before APA all night.
Yeah, what, I went to that's like after the first exam, so all this is kind of but I think I got a better idea for all the production stuff now.
Okay, that's good. Awesome.
Yeah.
Yes, we do.
So
We have SI Friday, don't forget.
are you sure that he's not gonna include like any of the Gemini coupling or the value?
I can't say it for sure, but in my experience on the final, I don't think so.
Okay. Okay.
So yeah. This one? Oh, wait, this one. So she basically combined two main steps in there because let's redraw this guy. On the first step, that pH attack, nucleophilic attack, gets connected in there and we cup the electrons. So we're forming O minus and we added pH. But she combined the next step as well because we reformed the third one because we had a leaving group in here. So we kick it out. And that's how we end up with that ketone. If you have a leaving group, kick it out. Because we still have a carbonyl. Remember, reductions, we have to get rid of as many pi bonds as you can. Okay, no problem. Take care.